Hi everyone! In this final video on random numbers, I want to talk about normal distributions and also other distributions that are present in the NumPy library. We've previously seen two ways of generating random numbers. The first one, if I scroll up, was the integer methods or integers, and the second one was the random method. And both of these ways of generating random numbers are uniform in the sense that each number has an equal chance of appearing. But not all distributions in statistics are like this. The most famous distribution in statistics is a normal distribution, and this is not like this. The classical example of normal distributions is height in adults. So if you go out on the street and pick a random person, then the height of that person might be, say, 1 meter and 75 centimeters. If you pick a lot of people, you might find that something around that is the average, but it's not equally likely to find a person who's 175 as it is to find someone who's 140, as it is to find someone who's 215. People on the end of the spectrum, meaning people say adults lower than 150 or higher than 210, is really rare. There's a really short and easy function to make normally distributed random variables in NumPy. We can draw normally distributed random numbers. Let's actually try to model the height example. So let's do heights. And now I go to the random number generator and then use the method normal. And inside the normal variables, let me just shift tab here. I can specify a location, which is the same as the mean. I can specify a scale, which will be the same for those who know as the standard deviation. And I can also specify a size. So let's say with a height example that without researching this, let's say that for adults it's 175 for the height. And this is in meters. And then the standard deviation, let's say that it's probably something like 0.15 maybe. And let's say I pick 100 people like this. So here you can see it, and I think I guessed rather good. So you can see a lot of people in the range of, say, 175, 174, 71. A lot of people slightly over 180, 186 here, 160. This is very common. But it's really uncommon here, even if I run it multiple times, to find someone who's 210. And this models kind of the real situation that if you would see someone who's 2 meters and 10 centimeters, you would probably also notice. So, to get a good understanding of the normal distribution, it can be a good idea to plot this. And Steve has told you about several different plots, like the plt.plot, plt.scatter, and plt.bar. But there is also the plt.hist, which is called a histogram. So let's start by making a bunch of randomly normal distributed numbers. Let me just call it y for simplicity. RNG, normal. Again, we do exactly the same, 175, 0.15, and let's take 1,000 of them, so a bit more. Now, we use PLT. This is for plotting. Recall that we have already imported matplotlib. If I just scroll a bit up here, I have imported matplotlib here as PLT, so it's fine. So I do PLT, and instead of the ones you've learned about, like plot, scatter, and bar, then we also have hist. So first of all, let's just specify the variable, which is y, and then we can do plt.show. And here you have a histogram. You can see that the average is roughly here at 175, and then it becomes less and less usual to see people here. So it's very common to see an adult less than 140 or over 220. So let's add a title with plt.title, call this normal distribution, like this. Looks good. But you can also specify the bin size. So the bin size is how many of these should be grouped into one kind of bin. So a bin is starting here. It's one of these bricks here. So we can just experiment. Let's say bins equal 10. I think that's slightly more than what we had, but not that much. So let's do 20. Now you can see that we have a lot more of these small bins. And let's do quite a lot, so 50 is quite much. So you can see that it has this kind of bell shape where it starts low and then increases to a certain point, and then it decreases again. This is an important property of the normal distribution, that it's symmetric, meaning that you're equally likely to observe things below the average than above it. So this is the normal distribution, but if I just look at all the methods I have here, RNG dot, then I have a lot more. So here I am at NumPy's documentation page on the random generator, and here you can first of all see some information about this generator that we talked about and how to initiate it as we did, and so on, a bit about its connection to this lower level component called a bit generator. In any case, if you scroll down a bit here past the examples, then you can see all the methods. And we've seen quite a few of these. We've seen random, choice and shuffle and integers. So if you scroll further down, you can see a lot of distributions here, and we've just seen a single one of them, namely the normal distribution. So if you're really a statistics person, then this should be pretty familiar. If you're not, then that's completely okay. But this is just a lot of the common distributions that pop up around in different disciplines. So some of you might have heard of the binomial distribution, or the chi-square distribution, or the geometric distribution, or the gamma distribution. All of these are pretty common. I'll not go through any more than the ones I have, because they all work more or less the same. So for instance, if you look at the binomial distribution here, then it says that it draws samples from a binomial distribution, and it can pass in parameters n and p in the usual binomial distribution, if you know what that means. Hey, and welcome back. So in this video, we're going to talk about statistical functions in NumPy. If you remember quite a few videos back, then I talked about aggregate functions. So aggregate functions in NumPy are functions that take in a NumPy array and return a single number. And basic statistical functions are typically all like that. So they're just a special case of something we've looked at previously. We've actually seen one of them. So we've previously seen the mean, or sometimes called the average, of a vector. So again, let me just initiate my favorite array. And we can then print out the mean of the array by using np.mean and passing in the array. You can see that the mean is 18. This is one of them. We've seen this previously. There are also three more that I want to show. One of them is the standard deviation. So if I have an array, I can use the function np.std and pass in the array like this. And here I get a number, and this is what's called a standard deviation. So if you recall the example with a normal distribution, then we actually had to pass in something here as a second argument, and this is essentially the standard deviation. So this is how much of a spread it has. So if you place a large number here, it can be good to just visualize this, let's say 0.5, then this here is a lot thicker, so it's more spread out. If you do it like an extreme amount, can be a bit hard to see here because Matplotlib automatically readjusts the axis so it looks kind of the same. But if you see here, then it really goes now from minus 2.5 to like 6 meters. So it's pretty spread out. So this was what we had. And now if you compare, the standard deviation is actually just 0.15. So it's just from 0.75 all the way to 0.6. So this is the distance of the standard deviation. So it's how much it spreads out. And you can find that of any array. And you can do it easily in NumPy by just doing the std here. This says that the spread here is 12, which seems kind of reasonable, so most values lie within 6 and 30. There is also a related notion called variance. And variance is just a square root of the standard deviation. So let me illustrate this so we can write squared std. And let's do np.std array and square this. This is one thing you could do, but you can also do the variance function. So this is np.var. And you can see that if you run this, then you get precisely the same thing. So you can either use the variance function or just square the standard deviation. It's completely up to you. This thing, the variance, kind of measures the same in the sense that if you know the variance, then you know the standard deviation is just a question of squaring it or not. But sometimes the variance is more natural in calculations, while the standard deviation is more natural to represent or present the data, as this is in some sense in the same scale level as the mean. The final function I want to talk about is the median. So the median is the middle observation. So let's go up to our function here and say you want to find the median of this. It's especially simple if it's already sorted as it is here. Then you just throw away that element, more or less, and the largest. Then you throw away the second smallest and the second largest all the way until you get to the center here. If you have one thing remaining, then that is the median. If you have two things remaining, here 15 and 16, you take just the average of those two. So that would be 15.5. So we can check this, of course, in NumPy by using, I guess, what you would expect, namely the median function. So we can do np.median and then do this on the array. And now we can see it's 15.5. It's really easy to read off if it's already sorted, but if it's not sorted, then this is a really convenient and easy function to get the median. I really want to point out something that I think is really important. So let me print it more properly by saying the median, and then print this. We also previously had the mean or the average. Let me print that out. like this. It's really important that these two are not the same. This is often confused for beginners, and that's completely natural because they both give some kind of measure of what's the middle of all of my observations, but they give it in different ways. So the median is by arranging them and picking the middle one, and the mean is simply by averaging all of them. If you want to really convince yourself that this is different, well, first of all, you can look at the numbers and say, yeah, these are clearly different. If you want a more extreme example, which is of course very silly, but it helps me remember it, say that you go up to someone who's selling chocolate, and they sell 3 bars of chocolate. First bar costs $0. The second one also costs $0, but they also have a third one. That one costs $100. So you have 2 free ones and one that costs $100. In that case, I'm just writing this as comments. The mean will be 0 plus 0 plus 100. So you sum all of them, and then you divide by the number of observations. So this is 1/3 times this nonsense here. And as you can see, this is roughly equal to 33, right? But if you do the median approach, then you first remove the lowest one, which is 0, then you remove the highest one, which is 100, so you removed one at each point, and you're just left with 0. So they're completely different. So the mean here would represent the seller just pushing a chocolate at you at random, just you have to pay for this. Then this would be the average amount you would have to pay. But the median would tell you that if a typical person went over, they would typically pay 0, in the sense that most people will pay 0, namely 2 out of 3 people. So they're just different measures of finding kind of center in your data. This is what I wanted to say about statistical functions in NumPy. In the next video, we're going to look at a really nice function for discovering how many unique values there are in an array. Hi, and welcome back. So this will be a pretty short video where I just explain to you how to find all the unique values in a vector. So let's start by just producing a vector. So let's do np.array. Let's just do a variation of my favorite array. So let's say 4, but I have some repetition. Again 4, I have some 8s, and then I have 115, then I have 3 23s, and I have 4 42s, like this. Say now that I just want the unique values here, not the duplications. I could do a for loop, but there's also a really neat function, which is that np.unique, then pass in the array, and this returns all the unique values. So you can see here that I get my standard array except for the number 16, which is not present here at all. And that's more or less it for this video, except that there is a really nice optional argument that we can pass into this unique function here. Say now that I want a plot of how many of these individual values appear. So you should have some kind of bar plot, as Tina told you about, where this here should have the height 4, this number here should have the height 2, this number should have the height 3, this number should have the height 1, and so on. So how can we do this? There are, of course, manual ways of doing this, but also there is an optional argument that you can pass in here. We just scroll down, and this is the return counts. This is by default set to false. So let's just do it here. We have the return counts variable and set this equal to true. Now you can see that I get back 2 arrays returned as a tuple. The first one is the one I got previously, and the second corresponds to how many of these appeared in the array. Since I have a 2 here, that indicates that 2 of the value 4 appeared, namely here. Doesn't matter if it's sorted or not, the original array will still pick up the same information. So that is really convenient because now I can draw a bar plot. Since they return a tuple, I can do what's called tuple unpacking sometimes, which is to just say I have my unique values, just call it counts, and then do this thing here. So let me just copy it. And if I do it like this, then this value here will be assigned to the first one, and this value counts will be assigned to the second. So let's do this. And now I can do plt. Remember that I have imported matplotlib as plt in a previous lecture. Then I can do plt.bar. As Tin told you about, and for x values, I would have my unique values, and for y values should be how many of them are, namely the counts. And here we can see the bar plot. And the highest bar is here at number 42. This signifies 4 because I had 4 entries of 42. So the fact that you can use this optional argument to return counts is somewhat new. I think this came about in NumPy 1.9, so make sure that your version of NumPy is higher than that. If you installed NumPy through Anaconda in the beginning, then definitely it will be higher than this, but you can always, as a side note, you can always check your version by just doing np._version here you can see that I have 1.18. So usually there are only minor updates from say 18 to 19, but actually if you go from like 1.9 to 1.18, then there are quite a lot of things that have changed, so you should try to keep it up to date. So that's the np.unique function. It's really easy to remember and it's really easy to use, so I love it, and I hope you do as well. Thanks, and I'll see you again in the next video.